I'm Guillaume Barré, and I'm postdoc here at Université Laval. I work with Crystal, Crystal Laflamme, Georges Baudin, and also I will present you some data I get with Jean Gauthier from Juan Aranda and Pierre Cartini, multiple sulfur isotopes. I did the multiple sulfur isotope with Pierre Cartini in Paris. So I will talk today about, of course, multiple sulfur isotopes, seawater sulfates, and Archean VMS. So just to start, a quick update about the laser ablation system compared to the ICP-MS triple report we have here now at the university. So the laser ablation system was installed last October, so it's working now. And we are currently developing the sulfur isotopes, a new method of sulfur isotopes in situ. So right now we try to determine the delta 44S, and we developed new standard because there is yet no standard for laser ablation for sulfur isotopes. And with the first test we have right now, we have a reproducibility on the delta 44S signature on the standard on barite of about 1 per minute. So just a quick update about that. And now go back to the VMS deposit. So the problematic of this project was we know that sulfate from the seawater has an influence on VMS deposits. So we know that the seawater, the sulfate from the seawater infiltrates in the crust and then is reduced by the thermochemical sulfate reduction, the TSR, into H2S. And there is a mixing zone where H2S from the basaltic H2S and the TSR to H2S is mixed, and this is recorded in the sulfide in the VMS. But the question here is an example of Proterozoic VMS. So the question here is, can we track the influence of the seawater in Archean VMS, and can it be used as vectoring tool to target new VMS deposits? So for that, we need a well-preserved and well localized sample on VMS deposits. So for that, for well-preserved VMS, Archean VMS deposit, so we target VMS from the Noranda camp and from the Matagami camp. So in detail, last summer, we sampled, so in the Matagami camp, we sampled the Maclot Deep mine. And in the Noranda camp, we sampled different outcrops of VMS deposit and Exalites. And to note that all these VMS and Exalite are dated at around 2.7 billion years. So we can compare them. So we sample exactly 3 different types of deposits. So the first one is a subsea floor replacement VMS. It's a Maclot Deep mine. The second type corresponds to a seafloor, we say a classical seafloor VMS deposit. So from the Noranda camp with Amulet, Moosehead, and an outcrop 1244. And the last type of deposit we sampled are Exalites. So different outcrops of Exalites in the Noranda camp, and also Exalite directly linked with VMS deposit. So just a quick overview of the petrography. The mineralogy we can find in these different VMS and Exalites. It's dominated by pyrites in all of the outcrops with sphalerite, chalcopyrite, and plus or minus pyrrhotite and galena, really rare galena. So we found approximately the same mineralogy in all the samples, but there is different proportion of each sulfide, even in a single deposit. So it's difficult to use only petrography as vectoring tool. So that's why we go with multiple sulfur isotopes to see if there is a variation of the isotopic signature depending on the type of deposit. So a really quick overview of the different sulfur isotopes there is. So there is 4 stable isotopes for sulfur: 42, 43, 44, and 36. So the common isotopic signature used is the delta 44s, but here we will use also the delta 43 and delta 46. So this I will be really quick on that with all these equations. Sorry for that, but just to explain, because I will use the capital 43 as the notation, which you just talked about that just before. It's just to say that it's a direct relationship between the delta 43 and delta 44, and it just this notation helps to see really small variation of from this mass dependent plan. So here are the first results I have. We get, and so here it's the results on the Macleod deep mine. So it's as I say, the subseafloor replacement VMS deposit. So we expected not much influence of sulfate seawater here, and it's exactly what we get. So it's mostly data value of typical magmatic signature. So as expected, there is no or really limited influence of the sulfate from the seawater. The other VMS deposits, or the seafloor VMS we sampled from the Noranda camp, here is the Amulet, the Mused, and the Outcrop 1244. So they're all in the Noranda camp. And here we see a slightly variation. Oh, I just forget to say that this small range we can observe in the Macleod signature, it's mostly due to just to a fractionation between minerals, between salarite and chalcopyrite, and it's just linked to temperature. And here, the main difference is that we observed a depletion on the capital 43S signature, coupled with an enrichment in the delta 44S. So it's really we interpret that as a mixing between a magmatic signature with an influence of the sulfate seawater. So it's really interesting for that. So we have already 2 different signatures between 2 types of VMS deposit. And just to talk about the temperature, as you know, we can use stable isotope to determine the temperature of crystallization between 2 minerals. So here, for example, between pyrite and salarite, we know that the fractionation is temperature dependent, but for that, to determine the temperature, the requirement is that the 2 minerals have to be at isotopic equilibrium. And thanks to multiple sulfur isotopes, it's possible to determine if 2 minerals are at isotopic equilibrium or not. So, and it's really important to determine that with multiple sulfur isotopes, because, for example, here with an example from Macleod deep, with 2 levels of the massive sulfides, with pyrite and salarite with relatively similar texture. One is at isotopic equilibrium, but the other is not. So for that one, we can't determine the temperature, but here we can. So here we determine a temperature of 400 degrees C. So with a similar paragenesis, it doesn't mean that we'll be at isotopic equilibrium. So on the 9 mineral pairs we arrived to have, only 4 are at isotopic equilibrium. So there was the Macleod deep, there was 2 temperatures, one at 380 degrees, the other one at 400. At Amulet, it's a bit higher, and that's still a bit higher, 460 degrees. So it's just something I wanted to show you, that it's possible to determine the temperature of crystallization of massive sulfide, but we have to determine if they are at isotopic equilibrium first. So let's continue with the last value we obtained on the Exalite. So it's a bit more complicated because there is 3 different type of value on Exalite. So with depleted in CAP43S value, some when the other are positive, present positive CAP43S value with a huge range on the delta 44S. But this group here with the depleted CAP43S value is really interesting because it means that there is a really important sulfate seawater influence on this exalite. And as you can see, it corresponds to some exalite with a direct link with pillow lava. So we know that there is an influence of the seawater here. So, but now how to explain this variation between the different type of exalites? So we can check the location of the exalite from the different VMS deposit, for example. So here in the Noranda camp, there is, it's easier to see on the cross-section, but that the exalite with a really depleted CAP43, so with a huge influence of sulfate seawater, are here and here, and the VMS deposits are we sampled that here and here. So they all are linked, they all link to the main contact tube, so the same stratigraphic layer. So there is a direct link between the VMS and the exalite here. But when we look to the two other outcrops with really unreached CAP43S value, so with no influence of sulfate seawater, they are not on a similar stratigraphic level than VMS deposit. So it can explain why they don't have the same signatures than the other exalites. So we can separate in four specific groups the different signature we have. So there is the sub-seafloor replacement VMS, the seafloor VMS, the exalite close to VMS, and exalite far from VMS. So it's really interesting. It means that there is a specific signature, isotopic signature for each type of deposit. So we can say that we can use multiple sulfur isotopes to target if we are far or not from a VMS deposit. So just to conclude, I will conclude just with this sketch. So to try to explain why some exalites present really important sulfate seawater influence and when some other are not. So for the sub-seafloor VMS deposit, of course, it's because there is no direct influence of the seawater. In seafloor VMS, there is influence of the seawater that infiltrate into the crust, the mixing zone between the magmatic and the TSR-derived H2S, and we can record a mixing signature of the seawater and magmatic signature in the massive sulfide. And the exalites that which are close to a VMS deposit, there is a direct link with between them. And here, the temperature allowed to reduce almost all the sulfate from the seawater. So and there is no direct influence of magmatic fluids. That's why there is a huge record of the seawater's signature in these exalites. And for the exalites that which are far from a VMS, it's a bit more complicated, but some papers talk about probable kind of sedimentary influence, possibly with bacteria, but there is no evidence of that here. But so maybe kind of digenetic influence, but that's something we have to discuss more in the future. So that's all for me. Thank you. If you have any question.
Thank you, Guillaume.